So we have obtained the J01 matrix. Okay. So similarly, I will just write all these matrices. So this is the exercise. So maybe I will write the answer. Okay. So J02 will be 0, 0, I, 0, 0, 0, 0, 0, I, 0, 0, 0, 0, 0, 0, 0. Okay. Then J03 will be 0. Rest of all elements are 0 except I and I here. All are 0. Similarly, you have this Jij's. Okay. So Jij, so J12 will be 0, 0, 0, 0, 0, 0, minus I, 0, 0, I, 0, 0, 0, 0, 0, 0. So you can see that J12 is basically J3 rotation matrix. Okay, it's this part. If you concentrate on this part, it's just J3. And then J13 will be, there will be 0 everywhere except these entries, minus I here and I here. Okay, except that everywhere it is 0. Okay, and J23 will be 0 everywhere and minus I and I here. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So once you know all these matrices, J01, J02, J03, J12, J13, J23, you know basically J10, J, sorry, this is, I think there is a sign somewhere, there is a sign problem. Let me see. Yeah, correct, I think. Okay, yeah. So if you know these matrices, you know J10, J20, J30, etc. Okay, because they are related by antisymmetry. Okay, fine. So the next thing, okay, is to determine the commutation relation among, so the commutations relation among J alpha beta, okay, or J alpha beta. There is no difference as such. Okay, so I want to know what is commutator J alpha beta and J, say, rho sigma. Okay, or J mu nu, because I used in my calculation J mu nu and J rho sigma. Okay, so let us evaluate this. So by definition of commutator, it will be J mu nu, J rho sigma minus J rho sigma and J mu nu. Okay, now you substitute, we know what is J mu nu. Okay, basically you have to use this form. Okay, you have to use this form. So this is what we are going to do. Okay, so let us say that I want to calculate commutator between J alpha beta, okay, and beta sigma. Okay, basically in the, if you give the indices to this, okay, you will write here alpha beta and beta delta something. Okay, so that will be suppose you want to determine alpha and delta element of this. Okay, then what will be this? Okay, j, so this will be alpha delta element j alpha j mu nu j rho sigma, its alpha delta element. Okay, this will be j mu nu alpha beta j rho sigma beta delta minus j rho sigma, okay, beta delta and j mu nu, okay, alpha beta. Okay, so this is what I want to calculate. So this is the commutator. Okay, this represents the commutator and this represents alpha delta entry of that commutator. Commutator of two 4x4 matrices will be a 4x4 matrix, right? So let us see. Okay, so let us see. Yeah, so we know the form of j mu nu alpha beta, explicit form. Okay, you will substitute that and simplify. There is nothing much to do. Okay, you know j mu nu alpha beta. Okay, so j mu nu alpha beta is what? Now instead of upper mu nu I have lower mu nu, so it will be eta mu beta. Okay, eta just a minute. Yeah, so eta mu beta delta alpha nu minus, so I times eta nu beta delta alpha mu. Okay, and similarly for j rho sigma. Okay, j rho sigma beta delta. So you substitute that. Okay, if you are in doubt with this notation, you can also use commutator of j mu nu and j rho sigma. Okay, there is no problem. Okay, essentially the result will be same. Okay, so you write the same expression for j rho sigma beta delta and just substitute it here, okay, and simplify. Okay, so let us do that. But I have done for upper rho sigma. Okay, upper indices I have done everywhere for upper indices. Why? I don't know why I'm bothering about lower indices. Okay, let us see. Okay, so let us do it for upper indices. There is not much difference. So j mu nu alpha lambda j rho sigma lambda beta. Okay, let me simplify this. Okay, so this will be, okay, minus, so there is a I in each definition, so there will be minus, okay, and then j mu nu alpha lambda, it will be eta mu alpha delta nu lambda minus eta nu alpha delta mu lambda. Okay, this will be this term, then j rho sigma, so j rho sigma will be eta rho lambda, okay, and delta sigma beta minus eta sigma lambda delta rho beta. Okay, so this is minus this into this, this into this, this into this, this into this. Okay, so it will be eta, so alpha will be, so let us see, so this lambda delta, so this you can write as eta mu alpha, eta delta nu lambda, eta rho lambda will be eta nu rho, okay, and delta sigma beta, okay, minus eta mu alpha, okay, delta nu lambda, eta sigma lambda, so it will be eta nu sigma. It doesn't matter whether I write eta nu sigma or eta sigma nu because it is symmetric, okay, delta rho beta, okay, plus, sorry, minus eta nu alpha, eta rho mu, delta sigma beta, plus eta nu beta, sorry, eta nu alpha, eta nu alpha, okay, eta sigma mu, delta rho beta. Okay, so this is product of these two. Okay, so you can further simplify it. Okay, so you will get minus, okay, eta mu alpha, eta nu rho, okay, delta sigma beta. Okay, eta mu alpha, eta nu rho, delta sigma beta. Okay, so you can write that in the following way. Okay, so I can just a minute. What have I done here? Eta rho alpha. Just a minute. Yeah. So you can write this expression in the following way: eta rho alpha, eta sigma mu, eta rho alpha, eta sigma mu, delta nu beta, minus eta rho alpha, eta sigma nu, delta mu beta, okay, minus, I will write this and I will explain how I obtain this. Eta sigma alpha, eta mu rho, okay, delta nu beta, plus eta sigma alpha, eta nu rho, delta mu beta. Okay, fine. So you see this here. What are the summed indices? Summation indices will be lambda only. Okay, that lambda is nowhere. Okay, here. Okay, so this term is actually coming from I have replaced nu by alpha. Okay, nu by alpha. If I replace nu by alpha, I have to replace alpha by let us see, nu rho. Okay, so nu rho is not coming anywhere. Okay, so let us see. I forgot how I obtain this term. Eta rho alpha, eta rho alpha. So nu is replaced by, oh sorry. Okay, so basically I don't have to write this term. Okay, so this correct. Okay, so this is the result. Yeah, so this is the result for this product. Similarly, you write the expression for j rho sigma lambda beta, okay, j rho sigma lambda beta. So I can write this as j rho sigma j mu nu alpha lambda, j rho sigma lambda beta, and j rho sigma alpha lambda and j mu nu lambda beta. Okay, this will be minus eta rho alpha. So now I am writing this product is this one. Okay, but we have to take commutator, so there will be another term minus of another term. Okay, so that term I am writing. Okay, so eta, so j rho sigma alpha lambda j mu nu alpha beta will be eta rho alpha eta sigma mu delta nu beta minus eta rho alpha eta sigma nu delta mu beta minus eta sigma alpha eta mu rho delta nu beta plus eta sigma alpha eta nu rho delta mu beta. Okay, fine. So I have two terms in the commutator, this one and this one. Okay, fine. So you see j mu nu j rho sigma, its alpha beta entry will be j mu nu j rho sigma, its alpha beta entry minus j rho sigma j mu nu its alpha beta entry. This will be the commutator. Okay, j mu nu j rho sigma alpha beta entry will be j mu nu alpha lambda j rho sigma lambda beta minus j rho sigma j mu nu alpha beta entry will be j rho sigma alpha lambda j mu nu lambda beta. Okay, and these two terms are this one and this one respectively. Okay, right? So this one and this one, not this one. So expression for this is this entire term, expression for this is this entire term. Okay, now your job is to substitute this expression and this expression and do subtraction. Okay, so if you do that, okay, there will be some simplification, okay, some algebra you have to do. Okay, so I will give you the result. Okay, it's simple, some terms will cancel. Okay, if you cannot do it, please tell me. Okay, so you have to subtract this term from this term, and there will be some reshuffling of indices that you need to do. This will also teach you about tensors. Okay, how to reshuffle the indices. So if you do that, you will get the result. Okay, so this commutator will be I times. Okay, so it will be what you will get is minus eta nu rho minus I times j mu sigma alpha beta plus eta nu sigma minus I times j mu rho alpha beta, okay, plus eta mu rho minus I j nu sigma alpha beta, okay, minus eta mu sigma minus I times j nu rho alpha beta. So what you need to do, you have to subtract those and write it again in terms of generators. Okay, so this will give you, okay, so now if you throw away these indices, okay, now if you want to write general commutator j mu nu j rho sigma, then this expression will be, okay, I times eta nu rho j mu sigma minus eta mu rho j nu sigma minus eta nu sigma j mu rho plus eta mu sigma J nu rho. This you can do. Okay, please do this from this step to this step. Okay, so this is the commutator of generators. Why this is useful? Okay, the reason is following. Suppose if I define, okay, why, so at first hand it looks very messy calculation, okay, but if you practice with this kind of thing, you will, it's not that difficult. Okay, why this commutation relation is important? Okay, the reason is following. Suppose if I define two matrices, two set of matrices, define, okay, Ji and Ki in the following way. Okay, Ji is equal to half epsilon ijk jjk. Okay, where this jjk is same as this one. Okay, same as that expression for our j mu nu, but mu nu restricted to special indices, ij's. Okay, so here these ij's, I represent special indices. Okay, so ji is half epsilon ijk jjk. Remember, this is 4 cross 4. This must be 4 cross 4. And I define ki to be, okay, ji0. Okay, so how many matrices are there? So no matter what happens, you should have 6 generators. So I runs from 1 to 3. So there will be 3 Ks. Okay, and I runs from 1 to 3. So there will be 3 Js. Okay, so J's and Ks. Okay, 6. Okay, I have written this in slightly different form. Okay, clear? So I define Ji to be half epsilon ijk jjk. So jk is summed over, and ki to be ji0. That's it. Fine. Now, if you take this commutator ji jj, okay, is same as taking, if you know the commutator of jjk and j say lm, okay, you can calculate commutator of jij, right? Okay, so what you need to use, so our job is to evaluate this commutator now. What is this commutator? It will be 1/4, okay, half and half, 1/4, okay, epsilon ji, epsilon I lm, okay, and jj, epsilon j pq, say pq, where all these are special indices. Okay, then this will be commutator of jlm, commutator with say pq. I know what is this commutator because I know general expression, right? Okay, I know what is this commutator. Okay, what you will get is the following. Okay, you will get the expression like this. You will get the expression like this, the following. So you will get this will be, if you substitute that commutator, you will get minus I. Okay, this 1/4 factor will disappear. I lm epsilon j q, okay, m is summed over, okay, and j l q. This is what you are going to get. Okay, but epsilon. So this is the commutator of Ji Jj. Okay. Now epsilon ILM epsilon JQM will be minus, we know this expression, product of two epsilon, so it will be minus delta IJ delta LQ minus delta IQ delta LJ. Okay, so you substitute this relation here. Okay, what you will get, this is equal to JIJJ, then will be equal to minus I times epsilon IJK JK. This is what you are going to get. Okay, and you can see why I did this. This is your usual angular momentum algebra, angular momentum computational relations, right? So Li Lj is I times epsilon IJK LK, but here it is down, so I can take this, it will be just delta JK is nothing but minus JK. Okay, so this minus sign will cancel and you will get usual commutation relation. So part of the commutation relation, okay, this is the main commutation relation between the generator of Lorentz transformation. One part of it is nothing but the angular momentum commutation relations, usual angular momentum commutation relation. And that is not surprising because rotation group is a part of your Lorentz group. Okay. So part of the commutation relation is this. The rest of the thing, okay. Now what I want to do? Commutator of Ki Kj, okay, and then commutator of Ji with Ki. Okay. So rest of the commutation relation will be Ki Kj is equal to, so I can just write the result. Okay. Ki Kj will be equal to I times epsilon IJK, okay, JK. Okay, note that it's not KK, it's JK. So Ki Kj commutation relation gives you JK. So commutation between Ki Kj is JK. But what is this Ki? If you notice, Ki is defined through Ji0. And what this Ji0 roughly represents? We have seen J10 represents what? Or J01 represents what? J01 is a generator for the boost along X1, right? This is what we have seen. J01, okay? So if you do this, okay, what we got? J01 generates this. And what is this? This is just a boost. Transformation of X0 component under boost along X1. Okay? Similarly, this will be boost along X2 direction. Generator of boost along X2 direction. This will be boost along X3 direction. And so on. This will be concluded as rotation about z-axis. This will be rotation about y-axis, and this will be rotation about x-axis. Okay, so Jij is minus epsilon minus I epsilon ijk jk. Ki kj is I times epsilon ijk jk. And the rest of the things jj ji kj, this commutation relation will give you minus I epsilon ijk kk. Okay, what these commutation relations are telling you? So I will rewrite the first commutation relation. Okay. Commutation between two rotation is a rotation. So if you take rotation and if you consider generator of those rotations, and if you take commutation between two different generators, okay, so your rotation, this represent rotation about I-axis, this represent rotation, generator of rotation about Z-axis. If you commute them, you will get a rotation about K-axis, generator of rotation about K-axis. So rotation commutations gives you the rotation. Boost commutation gives you the rotation. Two boosts do not give you the boost. Okay, they give you rotation. So if you take the generator of two boosts, then their commutation relations, the commutation relation give you a rotation. So if you apply, you have a frame here, you apply boost and you go to another frame. Okay, clear? So this is some boost. Okay, suppose this is okay. So for simplicity, let us consider a frame and let us apply boost along x1 direction. So you get from here to here. Okay, so this is K1. This is generated by K1. Okay, then you consider frame and you consider boost along second direction. So this is achieved by K2. Okay, so you first apply K1, then consider K2. Okay, so you apply K2 and then you apply K1 and subtract from that result applying K1 first and K2 later. Okay, you will get a rotation. That is what this tells. Okay, and if you consider rotation and boost, you will get a boost. Okay, clear? So in this form, okay, this is the most general commutation relation between rotation. These are just a convenient way of writing the rotations, the commutation relation for Lorentz transformations, generator of Lorentz transformations. This is just a convenient way. Okay, they tell you that if you take commutation between generators of rotation, you get a rotation. You take the commutation between generator of boost, you get a rotation. While you take the commutation between rotation and boost, you get a boost. So in this relation, all these the boosts and the rotation, they are mixed up. Okay, in this way of writing, the boosts are also in this way. The boost and the rotation generators are mixed up basically. That's why you are getting like this. Hmm? But the fact remains that if you take if you apply two successive rotations and take their commutations, you get a rotation. But that does not hold for a boost. Okay, clear? Hmm? There is an intelligent way to re-express these commutation relations in the following manner. Okay, suppose if I define, I will again redefine. Okay, so that I will do maybe later on, or maybe I can do it here also. Okay. Fine. So there is an intelligent way to redefine these k's and these j's in such a way that, suppose if I define these k's and j's in slightly different way, and I will call that as m and n. Okay, I will construct two operators m and n which are related to this vector k and vector j in some way. I will do that in a such a way that if I take the commutation between m and m, I will get m, some factor. like epsilon as it is, I will get n. If I take commutation between n and n, I will get n. But if I take commutation between m and n, I will get 0. Okay. One can find a suitable linear combination of k and j. One linear combination I will call as m and another as n, such that if I take commutation between m, I will get m. Commutation between n, I will get n. And commutation between m, I will get 0. If I succeed in doing that, okay, then what would that mean? That would mean the commutation relation for the generators of Lorentz transformations, okay, can be written as direct sum of rotation generators. Okay. This separately represents rotation, this separately represent rotation, and this is 0. Okay. So basically, I want to write in slightly different way these commutation relations in m and n form, so that I will get appropriate splitting, decoupling. Okay. This way of writing the generators is particularly useful when discussing the transformation properties of your Dirac spinor. We will come to. We will see that. Okay. Clear? So the story is not complete. I want to write these commutation relations in slightly different way. Why I'm stressing on the commutation relations? Because if you study rotation, okay, then you will come to know that all the properties of your state space, okay. So you consider now rotation, Jz and Z, okay, just rotation. Forget about the Lorentz transformation. Okay. If you know the commutation relation between Jz and Jx or Y, okay, and if you know the commutation relation between Jz and J square, okay, this is sufficient to build J plus, J minus, and action of J plus on Lm, action of J minus on Lm, action of Jz on Lm, and action of J square on Lm. These commutation relations is sufficient to derive the state space. You recall how you built these angular momentum states. You used only this information and the fact that these are Hermitians. That's it. Okay. Use this commutation relation together with the fact that they are Hermitian. It is sufficient to construct the state space. Okay. We are going to do same thing here. But only difference is that we are getting two types of angular momentum commutation relations. We will get two types of angular momentum commutation relations. And with slight imagination, you can think one commutation relation, one type of commutation relation will lead to spin up, spin down. Another type of relation will also lead to spin up, spin down. So it is not hard to imagine that how your 4 cross 1 Dirac spinor is going to transform. We are not going to imagine this, we will do this. Okay, but at this point one can realize somehow this 4 cross 1 structure is already appearing. Decoupled 4 cross 1 structure. Okay. For that, you should be absolutely sure how you constructed this state space, okay, from these commutation relations. Just by using commutation relations and the fact that these are Hermitians, it is sufficient to build a state space. This information is sufficient to build a state space. Okay, that's why I'm bothering about these commutation relations. Once I know what kind of algebra this generator, this commutation relation normally in the mathematical language is called algebra. Okay, so you have rotation algebra. Rotation algebra is given by the commutation relation between Li, Lz. Okay. Similarly, the Lorentz algebra will be given by this J mu nu J rho sigma. Okay, or Ji J with kids, okay, etc. Okay. This commutation relations is called algebra. Algebra of that transformation. So the commutation relation between the generator is called an algebra of that transformation, which whose generators are given in the commutation relation. Okay, but there is a but that you should be absolutely sure about the rotation. That I will assume you know everything about the rotation, that I will assume, and then I will go for Lorentz transformation. Okay, yeah. So this is half story. Okay, we have to construct the combination M and N in a suitable way so that there is some decoupling occurs. Okay, some of the things you will not understand at first glance. Okay, but if you practice, okay, and if you uh, think a little bit, it's not that hard. Okay, but before writing this algebra, okay, let us revisit again to our this Lorentz transformation written in this this exponential form. Okay, so in the infinitesimal form, I have identity minus I by 2 omega mu nu j mu nu. Okay, then if I apply this n times, okay, then I will get a result like rotation. I am not going to prove this. I will get a result exponential minus I by 2 omega mu nu j mu nu. Okay, fine. And I want to write this lambda omega in terms of this ji and ki. Remember how ji is defined? Ji is defined through half epsilon I j k j j k, and ki is j I 0. Okay, so I can easily write this relation basically in terms of ji and ki. Okay, so let us see how to do that. Okay, so let us concentrate on omega mu nu j mu nu. This will be equal to omega ij jij plus 2 times, see what is going to happen. So this is special part, then omega 0 I j 0 I plus omega I 0 j I 0, right? But this will add to this because of the antisymmetry. Okay, you can interchange 0 and I here, then you can interchange 0 and I here, you will get no sign change, and you can add this. So it will be omega I j j I j plus 2 omega 0 I j 0 I. Okay, I can do same thing here, but here ij's are summed over. Okay, so everything is counted here. Okay, fine. Okay, but remember the definition of ji. Ji is half epsilon I j k j j k. So what will be your j j k? Okay, j j k, to get the knowledge about j j k, what you need to do, okay, you just take, it will be 2, okay, and you multiply. Okay, so let me do it slowly. Okay, so this will be 2 times ji equal to epsilon I j k j j k. Okay, now I will do the following thing. I will multiply j epsilon I L M Ji. So I will multiply by epsilon ILM from the left. So I will get epsilon ILM epsilon IJK JJK, and summation over I is implied here. Summation of I is implied here. Okay. What is this? Okay, your usual product of two epsilon. So it will be minus delta I is summed out. So it will be delta L Z delta M K minus delta L K delta M Z. Okay, J J K. Okay, fine. So what is this? Delta L Z delta J J K. Okay, so I can replace J by L. Okay, so I can replace here J by L and K by M. So it will be J is replaced by L. So it will be L. K is replaced by J. So K is replaced by M, J, M minus delta LK delta MJ. J is replaced by M and K is replaced by L. So this is antisymmetric. So it will be minus 2 times delta L. Okay. So 2 will cancel. Okay. So JLM will be equal to minus epsilon ILM JI. Okay, fine. Okay, so I can, since there are two special indices, I can, if I take both up, there is no sign change, so it will be implied JLM equal to epsilon. There will be, yeah. So if I do that, then I will get minus epsilon JLM, so it will be ILM JI. Okay, fine. So you can substitute now for this expression, this expression. Okay, and here same similar kind of expression. Okay, so at the end, what you will get is the following. So if I substitute that, omega mu nu j mu nu will be equal to minus omega ij j epsilon I j k j k, okay, plus 2 times omega I0, okay, ji0, but ji0 I can write as minus, okay, so it will be minus ji0. Okay, so I will keep that. Okay, so yeah, so I'll keep that ji0 as it is, because ji0 by definition is just ki. Okay, ki is ji0, so I can, at the end I can just replace ji0 by ki. Okay, fine. So your Lorentz transformation will be exponential minus I by 2. Okay, so minus I by 2, so it will be plus I by 2 omega ij epsilon I j k j k. Okay, minus I, so it will be 2, so 2 will cancel, omega I0 j I0. Okay, and note that this omega I0 represents the ith parameter for your Lorentz transformation, and they are antisymmetric. Okay, so if I define, say, theta k, okay, some three numbers, theta k equal to omega, if I define theta k as half omega ij epsilon ijk, see, there is a summation over ij, so k is a free index. So I will, if I sum over ij, I will get just a one index object that I'm defining as theta k. Okay, so theta, if I define theta k like this, okay, and omega I0 as say eta I, okay, and by noting that ji0 is equal to ki, what I'm going to get, okay, lambda omega equal to exponential I times theta k jk, okay, minus I times eta k kk, or eta I ki. Okay, fine. So this is nothing but in your dot product notation exponential I theta dot j, okay, minus sign, because if I take this it will be minus sign, and plus I times n dot k, eta dot k. Okay, so this is the expression for generator of Lorentz transformation in terms of j and k. Okay, this j is not your usual rotation. Okay? It is connected to rotation, but it's not in that form right now. Okay, so I have skipped few steps. Okay, you try to fill it. If not, you ask me question, I will give you the step. Okay, I skipped few steps in this derivation. Okay, to try to fill it. If not, I will give you this. I will give the steps. Okay, but it is better if you do that, because in the exam, if you cannot do, then I will tell, and in the exam I will ask you something else then. Okay, so it's better if you do that. If you do that, if you don't ask me anything, if you do that, I will give that in the exam. I may probably give that in the exam. So in the exam you will succeed. But if I give everything, then in the exam I will ask something else. So please fill these gaps. Okay. So this is another convenient form for Lorentz transformation. Okay. This is the boost part, and this represents, I will not say rotation at this point, but at the end we'll see that this is indeed connected to rotation. Okay. Right. So I'll stop here. Okay. And then in the next class we will redefine that M and N type generators, and we'll see how the Lorentz algebra is broken up into two parts, two decoupled parts. Okay, fine. If you have any question, you can ask. So today was slightly lengthy class. Okay, so there are so much algebra involved. So if you have any problem, you can ask. Otherwise, I will stop. Any specific doubt?
Sir,
Hmm.
sir, we have this
Huh?
quantity. We have this quantity k that we
Ah.
defined j I0 equals to ki.
Ah.
Does this ki quantity, this one, does this k represent boost in
Yeah.
general?
Yeah. Ki represents the boost, right? So see how we define this ki. Okay. Ki is ji0. So you concentrate on k1. Okay. K1 will be what? J10. Okay. Clear? What is J10? If you go back, okay, J01 is this matrix. which generates the boost. Right? I showed that delta x mu, if you set all these parameters except 0, 1 to be 0, then what you will get? You will get this, right? This represents boost in x1 direction, right? Okay. This is the role of J01, but Ki is defined as Ji0. So it will be a negative of the boost. So it will be inverse boost, but it will be a boost. Okay. So we showed it just for I equal to 1. I explicitly showed what is the generator for J10 and what kind of transformation it will generate. This will generate the boost along one direction, x1 direction, or inverse boost. Okay. If you do it for 2 and 3, you will get boosts along x2 and x3. So these are basically boosts. Okay. And this part, you will see that this is actually a rotation. Okay. From the algebra, you can already see that. Okay. Ji, Jj is Jk. So this algebra is same as your angular momentum algebra. Okay. So, but I want to say something on this. Okay. After that, I will say that it is rotation. So in this case, here this relation tells you that the Lorentz transformation is made up of two parts, rotation and boosts. This part generates boosts and this generates rotation. But there is a problem. The problem is that your okay, I will tell you the problem maybe in the next class. It's not, the story is not that simple. Okay, in your rotation case, okay, this is written as, right, this is Hermitian. Because of this I, this becomes unitary. Okay, unitary transformation. Okay, u dagger u equal to 1. Okay, the story is not so simple in the case of Lorentz transformation. This part remains unitary, but this is not. This part gives you something. And reason you can trace back to the fact that these etas, okay, etas are basically the parameter for Lorentz transform boosts. Okay, eta 1, eta 2, eta 3. Okay, maybe I will again do this explicit calculation from this point onwards. So because it's not that I have to tell you something here. How I can say that omega I0 is eta I, that we have seen. Okay, but these eta i's are the parameter for the boosts. And this eta, if you go back to first part of this lecture, these etas are not bounded. Okay, it's run from 0 to infinity. That is basically the reason why I will not get unitary part. Okay, rotation part will give you the unitary contribution. If you set, suppose there is no boost, if you set eta equal to 0, all etas are zeros, then you will left with only rotation. So Lorentz transformation in that case is just a rotation. Okay, then in that case it will be unitary. But if you consider no rotation and only boosts, okay, you cannot construct a unitary representation or unitary form for these matrices. And it is a general fact about the Lorentz group, because the Lorentz group, because of these boosts, is non-compact in general. And for a non-compact group, okay, you cannot construct any finite dimensional unitary representation. That is the group theory statement. It is general theorem that for a non-compact group, it's not guaranteed. It cannot. It's a wrong statement. It's not guaranteed that the finite dimensional representation of non-compact group are unitary. It's not guaranteed. Okay? For that, some knowledge of group theory is required. But yes, indeed, these are your, as far as your question is concerned, these KIs represents boosts. Okay. Any other question? But please go through this lecture again. Okay, before coming to next lecture. Okay, otherwise, you will not. All these things will pile up. You will not understand. Okay. If it is becoming too heavy, tell me. Then I will take lecture. I will not take tomorrow. I will take maybe 2 days after. If you want time, you tell me in that way. Okay. But if you don't tell me, I will assume that you are reading. Unless you understand this lecture, you will not understand. Okay. Yes. Question. What you are asking?
Give us a day off.
Yeah, but in that day you have to do this. Okay. So I will give you a day, but it's not that you will just relax. Okay. Please do that. Please go through this lecture. Hmm? Okay. So I will not take
Okay,
tomorrow.
sir.
Then. Okay. I will take a day after tomorrow. Okay. Because now from now onwards some difficulty and some your algebra will become lengthier, your computations become lengthier. Okay, and don't bother about the exam. We will I may not give everything which I am going to teach in the exam. Okay? I am preparing you for the next semester, because anyway we lost this semester because of this problem of this COVID. Okay. So I'm preparing you for the next semester. Okay. It does not mean that I will not ask anything from this in the exam. But don't think too much about the exam right now. Okay. Just try to understand, because everything which we will do later on will depend on this. Hmm? So please be sure. Okay. Okay. Hmm?
Sir,
Huh.
sir, once we construct this M and N, we can then define corresponding operator for boost and rotation we have already, but for boost.
Yes. Yeah. The boost. So no. No. If we define M and N, the boost is still given by your Ki. Okay. What I want to do is the following. I want to decouple this algebra. Okay. I want to decouple this. I want an algebraic structure which is something like that. Commutation between same type of generators gives me a same type of generators, and commutation between cross generators, that means different type of generators, gives me zero. This is what I want. Okay, so that one can achieve. By doing that, what will be achieved is the following. Okay, so the Lorentz group is called by SO1 comma 3. Okay, and we have its algebra of SO1 comma 3. Okay, then I have here rotation group SO3. Okay, and I have algebra for SO3. Okay, what one can do is that if I manage to decouple this, then the result is that I have SO3 algebra, loosely speaking, SO3 algebra, direct sum SO3 algebra. So both are now goes to rotation level as a algebra wise. That decoupling occurs. It does not mean that the Lorentz group is SO3 plus digit sum SO3. It's not. Okay. Algebra. This structure is called algebra of the transformation or algebra of the group. Okay. That can be written as two separate copies of angular momentum algebra. Physically, M and N will not represent angular momentum. Okay, but the algebraic structure, the mathematical structure is same as your rotation structure. Okay, it will help us to build the state space. Okay, I'm not going into full-fledged group theoretical details. Okay, that's why maybe there will be some lag in understanding if from the group theory point of view. But as far as this is concerned, it is you can follow step by step. Okay. So maybe I will end this lecture, and maybe day after tomorrow I will take the next lecture. But please go through this lecture. If you don't understand, let me know. Okay. You can message me maybe this part we have not understood. Okay, you discuss among yourself, okay? And then come up with some common points. Okay, and you can text me these points we have not understood. Okay, then I will discuss those points. Okay, so I will end.